So here we have a series of problems on our nucleophilic acyl substitution reactions. And so we start right away with the addition of LAH. LAH we know is a reductant. It will reduce any carbonyl compound. In this case we've got an amide, and in the presence of amides, LAH is able to reduce them all the way down to the corresponding amine. Part B, we only have a single reagent. But that single reagent has a very reactive electrophile, acid chloride, and we know that acid chlorides will readily react with a number of different nucleophiles without any other reagents present. Well, within the same compound, we also have an alcohol. And so if that alcohol and that carbonyl are the right distance apart, then this will just close together in an acyl substitution reaction, form an ester. In this case, we call it a lactone because it'll be a cyclic ester. And so if we count our carbons here, 1, 2, 3, 4, 5, 6, we can see that the oxygen is 6 atoms away from that carbonyl. And so we can bring that together, closes, and we form our ester. Part C, we're starting with a dicarboxylic acid, in this case succinic acid. The conditions here, alcohol and heat, are the Fischer esterification conditions, which will convert carboxylic acid to an ester. Since there are two of them, it would be reasonable to expect that both of those acids will get converted into esters. Part D, we have a carboxylic acid with an amine in the presence of DCC. Recall that DCC is probably our most straightforward way to convert an alcohol into an amide. So the amide, the one that's above the arrow, will do a displacement of that OH group to give us our product. And then part E, we have an acid chloride with an amine. The same way in part B that an alcohol can displace the chloride of an acid chloride to form an ester, an amine can do the same thing to form an amide. Part F, we have again our DCC conditions that form amides. And this one you might notice again is very much like part B. The NH2 group and the electrophile, the carboxylic acid, are within the same compound. So it will, just as it did in the previous question, close to form a ring. Now, if you're wondering, will that always happen if they're internal? The answer is it depends on a lot of things, but mostly it depends on how big the subsequent ring size would be. If that ring size is going to be 5, 6, 7 carbons, then extremely likely to. Other ring sizes, especially smaller ones, definitely less likely and can result in other reactions. G is also the addition of an amine in the presence of DCC, but this amine is actually tertiary. And tertiary amines, because they don't have any hydrogens that we can remove, won't react here. And then part H, addition of hydroxide to an ester. These are very general basic hydrolysis conditions. And so the result here is that we can form a carboxylic acid. All right, question 2, we're looking for some retrosynthesis. I've given you some compounds, and the question becomes, how do we form these? Now, part A, we have an amide, and we've just seen a couple times, again, you can always form an amide from an amine and then a carboxylic acid or an acid chloride. But what that means, I'm going to make this a little bit bigger so I can draw on here better, is it means that we're going to be essentially breaking that bond. And so the right side will have our aromatic ring and our carbonyl. Now what group's going to go over here? Doesn't really matter. It could be a carboxylic acid, it could be an acid chloride. Either one of them will work very, very well in this case. I'll put a chloride in here. I think if you look at the key that I probably have posted for Blackboard, on Blackboard for this exercise, I think I've done a carboxylic acid on there. Either one works, and then we just need the amine as the other piece. Just keeping our carbon groups intact. Part B, we have an anhydride, and so we could break this anhydride up on this side or this side, either one. Now we've learned that anhydrides are generally formed from carboxylic acids and acid chlorides. So we just pick the pair of compounds depending on which side we choose to break it up on. So one possible answer, if we broke it up here, we'd get the acid chloride on the right. And the carboxylic acid on the left. And part C, very much like a couple of the examples we did previously, when we break it here, it's still going to be a single compound, but it'll end up as an acyclic starting material. All right, now we've got a couple of synthesis questions. And this one looks fairly complex. You can see that there's definitely a lot going on here. We've got multiple oxygens that were present in the starting material that are gone. We've got a bunch of extra carbon groups. So how do we start this one? Well, when I see that nitrogen on there, that nitrogen makes me think that we probably had to have an amide at some point. So maybe I got to here. By taking this amide, oops, and not LDA, let's use the correct reagent, LAH, and we know that that will reduce our amide into the amine that we see above. Now, why do I think it has to be an amide there? Well, we need to get that nitrogen in, and honestly, at this point, we don't really know other ways of making carbon-nitrogen bonds. You might be thinking, could we have used an SN2 with an amine as a nucleophile? And the answer there is actually more complicated than you think, but in a lot of cases it won't work. Amines are actually too reactive for a lot of SN2 reactions. That's something we'll learn in the way at the end of this course, other ways to make amines. So for now, the best way that we know is to start with an amide and reduce it. Now, how do I make the amide? Well, I know that if I had a carboxylic acid, and I use DCC and this diethylamine, that'll form the amide. Now we don't have a carboxylic acid to start with, we actually have an ester. So most likely, then we could say that this ester could be formed from a hydrolysis, or the ester could, through hydrolysis, form the carboxylic acid that we need. So last thing we need to do in this situation is we need to get these two groups on there. That's all these extra carbons. And we could do that through a pair of alpha substitution reactions. Base and methyl iodide would put on the methyl group. And then again, base and benzyl iodide would put on that final group. Our second synthesis question, so we're starting from benzoic acid. And you can see, again, we need to get an amine in there. So we're probably going to make it from an amide, but we also have that alcohol. And so we can't have that alcohol necessarily present when we're making the amide because the OH group might react instead of the nitrogen. But we could instead say that maybe that alcohol comes from an alkene. And we could make that alcohol, which we can see is the less substituted alcohol. Through a hydroboration reaction. We could then make this amine from the corresponding amide. Reduced by LAH. And then finally, we could make this using the appropriate amine and DCC from the carboxylic acid. And then in question 4, we have some pairs of carbonyls, and we're trying to determine which one is the better electrophile. Part A, we have an ester versus a thioester. And in most cases, the better electrophile is determined on the ability of the leaving group. And here, the sulfur group actually makes for a better leaving group than the methoxy group. And because of that, this is the more reactive carbonyl. According to that logic, same thing in part B. The leaving groups are an O- next to a phenyl ring, so stabilized by resonance, or an O- next to a cyclohexane, not stabilized by resonance. Better leaving group, more reactive carbonyl. And part C, we can't get away with talking about best leaving group because the leaving group's the same in both cases. But nitrogen, we know, is electron donating. Adding more electron donating groups makes the carbonyl a worse electrophile. And so with less electron donating groups, we have our slightly better electrophile.